In this example, we're going to diagonalize the following matrix. Okay, so diagonalization is it's a way to factor a matrix. Okay, where if you look in this box here, okay, so we want to come up or construct A in terms of P, D, and P inverse. So the matrix P will contain well, actually, it's a matrix that will have where the columns of that matrix are the eigenvectors. Okay, and then D is the diagonal matrix, where the entries along the main diagonal will be will have the eigenvalues. Okay, and then we have P inverse. Okay, so the first thing we need to do is to obviously find. Okay, we need to find the eigenvalues. Okay, because those are going to make up for the main entries for D, for the matrix D. Okay, so the first step is to find. Okay, right, we need to find. Okay, the eigenvalues of A. Okay, so when we go back, okay, we need to, right, so we need to find the determinant of this system. Okay, now the determinant of A minus lambda I. Okay, so we have 2, 2, negative 1, 1, 3, negative 1, minus 1, negative 2, and 2. Okay. And minus lambda, so we have the identity matrix here, so 3 by 3 identity matrix. Okay. All right, so this is going to give us 2 minus lambda, 2, negative 1, 1, 3 minus lambda, negative 1, negative 1, minus 2, and 2 minus lambda. Okay. All right, so we need to go ahead and find the determinant of this, okay, of this matrix. Okay, so let me just put in so technically this is, right, we have the bars here. So we want to find the determinant of this matrix, okay. All right, so I'm going to use, I think it's easier in this case to do using cofactors, okay. All right, so let's do that here. So the determinant of this, okay, so starting down here. So I'm going to use the I'll use the first row here, okay. So we're going to have 2 minus lambda times, okay, the determinant of 3 minus lambda, negative 1, minus 2, 2 minus lambda. Okay, and then, so then we're going to have, let's see, I think I'm going to use, well, actually, sorry, I'm going to use the first column. Okay, not the first row. So we have minus 1 then, because we have positive and negative. Okay, so minus 1 times the determinant of 2, negative 1, minus 2, and 2 minus lambda. Okay, and then last one, okay, we have plus, actually it's going to be minus 1. Again, so I'm using the first column. So minus 1 times the determinant of 2, negative 1, 3 minus lambda, and negative 1. Okay, so now let's simplify this. So you have 2 minus lambda. This is going to be 6 minus 5 lambda plus lambda squared minus 2. Okay. And then minus, Okay, this is going to give us 4 minus 2 lambda minus 2. And then here we get, go ahead and distribute the minus 1. So I get 2 minus 3 plus lambda. Okay. All right. Okay, so now we can multiply everything out and simplify. Okay, so that's going to give us minus lambda cubed plus 7 lambda squared minus 11 lambda plus 5. Okay, so now we're going to set this. Okay, so we want to set this equal to 0 to get our eigenvalues. Okay, so solving this, it's going to give us lambda equals to 1. Okay, and this is actually a multiplicity of 2. And lambda equals to 5. Okay, so to solve this equation, you may want to review something from pre-calculus. Okay, so you can use the Descartes rule of signs, and then from there you can use long division to find the roots to this. Okay, all right. Okay, so step 2. So we found the eigenvalues. Now step 2 is to find the corresponding eigenvectors. Okay. All right, so let's start with lambda equals to 1. Okay, so we have to substitute this back into our, okay, substitute this back into here. Okay, so we're going to get 1, 2, negative 1. Okay. So 1, 2, negative 1. And then we're going to get 1, 2, negative 1. And then negative 1, negative 2, and 1. Okay, so we want to find the null space for this. Okay, all right, so this is, remember, this is the matrix corresponding to the homogeneous system. Okay, we're going to find the null space of this. Okay, so this, I'm going to go ahead and do the REF on this then. Okay, so this is going to give us 1, 2, negative 1, and then we have the row of zeros here. Okay, so then, okay, right, we have 1, 2, negative 1. Okay, just augment the 0 vector onto there. Okay. All right, so we have 2 free variables here and 1 basic variable. So we're going to let x3 be equal to, let's say, t, and x2 is going to be equal to, let's say, s. So t is a real value, and so is s. Okay, so then from here, okay, from x1, okay, x1 is going to be equal to 2, actually, it's going to be equal to, minus 2x2 plus x3. So that means, so since x2 is s and x3 is t, so we're going to get minus 2s plus t. Okay. All right, so that means, okay, we have, for x, we're going to have, for x1, we have minus 2s plus t. For x2, we have s, and for x1, sorry, for x3, we have t. Okay. Okay, and then this can be we can write this in parametric form. So we're going to have S, so S will be multiplied by -2, 1, 0. And then we can factor out t. So it's going to leave us with 1, 0, and 1. Okay. So our basis, okay, so the basis for the eigenspace, okay, are going to be these two vectors that you see here. Okay. Okay, for lambda equals to 1, it's going to be this vector and this vector, okay? So the basis, so we write this as a set, okay? So this is going to be part of our P matrix, okay? All right. So let's go ahead and I'm just going to go ahead and identify these. So this is going to be V1, and I'm going to call this V2, okay? All right. So let's find the eigenvector corresponding to lambda equals to 5. Okay. Okay. Okay, so for lambda equals to 5. Okay, so again, plugging lambda equals to 5 back into the system here, okay, we're going to get -3. Let's see, yeah. So -3, 2, -1, okay. And then 1, -2, -1. And then for the last row, we have -1, -2, and -3. Okay, so now, so let's do an REF on this. So we're going to get 1, 0, 1, 0, 1, 1, or 0, yeah, 0, 1, 1, and then 0, all zeros on the last row. Okay. All right, so, okay, so then we're going to solve for the null space for this system, for this particular matrix. Okay, so oops. Okay. All right, so just like before, okay, we're going to come up with our solution and then write it in parametric form. So in this case, we get one free variable. So we're going to let x3 be equal to t, okay, where t is some real value. Okay, and then x2, okay, so from here, okay, x2 is going to be equal to minus x3, which means that that's going to be minus t. And then from here we have x1 equals to minus x3, which is going to give us minus t. Okay, so now we have, okay, so we have x1, so minus t, x2 is minus t, x3 is t. Okay, so writing this in parametric form, okay, we have that we get minus 1, and 1. Okay. Okay, so that's our that's going to form the basis. Okay, so this vector here is going to be the basis for the eigenspace for lambda equals to 5. Okay. Okay, basis for the eigenspace for lambda equals to 5. Okay, so we can write this as, okay, the set. All right. Okay, so let's call this V3. Okay, so now we're ready to construct construct P now. So that's step 3. Okay. Okay. So we construct P, okay, from the vectors, okay, from the eigenvectors. Okay. All right. So from the, well, we're using the basis, right? The basis the basis for the eigenspace. Okay. Okay. So P, okay, so just a notation, okay, so we're going to say that P, okay, is going to be constructed by V1, okay. So let me write this a little bit bigger. So we have V1, V2, and then V3. So those are going to form the columns for P. Okay. So from there, okay, so for V1, we had negative 2, 1, 0. Okay. For V2, we had 1, 0, 1. And then for V3, we have minus 1, negative 1, 1. Okay. So here the order doesn't, the order is not very important. You could put V3 first, then V1, V2, okay? But then if we do that, we have to make sure that that it corresponds to the eigenvalues, okay, that we're gonna construct for D, okay? All right. So step 4, okay, that's gonna be the step 2, construct D. Okay, so we're gonna construct our diagonal matrix, okay, from the eigenvalues. Okay. Okay, so D, okay, so D is going to turn out to be, okay, so this is what I was mentioning earlier about the ordering of our eigenvectors, okay, since we put, so for V1 and V2, that came from the eigenvalue of 1, okay, so we want to put, okay, we want to put our eigenvalues, okay, we want to put the eigenvalue, if we had 1, okay, so we're going to put that here, okay, and since we're dealing with 3 by 3, then this is going to, D is going to be a 3 by 3 matrix. The other, right, and so since lambda equals 1 was a, remember that it was a double root, okay, we had, right, lambda equals 1 was multiplicity of 2. So we have to write it down twice, okay. So we're going to put the other, okay, so we put the other eigenvalue here, okay. All right. And then there, so now for the last, okay, for the last eigenvalue was 5, and that corresponded to this eigenvector V3. So we're going to put that into here now. So it's going to be 0, 0, and then 5. Okay, and so that's our diagonal matrix. Okay. All right. So now all we need to do is to find the inverse of P. We need to, okay? Okay, so remember that we have A is equal to P times D times P inverse. So P inverse, so we can calculate that, and you can either do that by, you can use a calculator, or you can do it by hand by augmenting the matrix P with the identity matrix and then doing the RREF on that, okay? So P inverse, okay, let's do that over here. So P inverse turns out to be minus 1/4, 1/2, 1/4, 1/4, 1/2, 3/4, minus 1/4, minus 1/2, and then 1/4. Okay. So that's our solution. Okay, so we know P, we know P inverse, we know D. Okay, so in summary, right, we had, okay, so we should be able to check that A, right? So if you take A, sorry, so A is can be written as P. So we have minus 2, 1, negative 1, 1, 0, negative 1, 0, 0, 0, 1, 1, times D, 1, 0, 0, 0, 1, 0, 0, 0, 5, times P inverse. Okay, so so if you multiply all those out, you get back the matrix A that we start out with. Okay, so this is a really nice factorization technique. Okay, and we can use this actually to solve systems as well, but we won't be looking into that. But there is a way to do that. Okay. All right, so this is so just going back, okay, so this process to diagonalize a matrix, first you got to find the eigenvalues of that matrix. The eigenvalues of that matrix is going to form the diagonal matrix D. Okay, and then once you find the eigenvalues, then you find the corresponding eigenvectors. Okay, and those are going to form the columns of P. So now, as I mentioned, the order is important. Okay, so, well, I mean, you have to keep track of your columns, because if you switch the columns here, then you have to switch the columns for D. Okay, so they should be entered. There should be a correspondence between the eigenvectors and the eigenvalues. Okay, for your D matrix. Okay, all right.